So now I want to do a bit of a demo just explaining how tasks, sort of their states work and also their sort of structure in code, and namely with FreeRTOS in mind, because this is what we'll be working with, and it's a very easy and simple way to get our heads around sort of threads and how we can make a program that's multi-threaded in a very simple way without getting into the complex like POSIX, pthread libraries and stuff for Unix operating systems. So we saw in the lectures that we have this sort of structure of task, sort of states. Now, I'm going to make a quick example that makes a few tasks in the ready state, and then we'll look at how we sort of send them to the suspended state, how they run when they block, and then how they're sort of made ready again. And so what we want to do first, we want to create a few tasks. And so I have the documentation here from this xtask create function, which we saw in the lecture slides. And sort of I want to start creating a few tasks, and then I'll look at the first parameter here, which is the task code. And so what this actually is it just requires us to write a function, which we then pass into this function call as a function pointer, which we won't even touch on in this course. But essentially, you just have to list or provide the name of the function that should be run as a thread or a task, as FreeRTOS calls them. And so we're going to create a couple of tasks here. We'll make one, we'll call one demo task 1 and demo task 2. Now, the tasks functions themselves have to have a certain form, because the function essentially has to take the form like this, in that it's a void function because it should never return. We saw in the slides there's a few sort of properties that a task should have. Is it should have some sort of endless loop that it executes. It should never kill itself, meaning that it doesn't return. It's sort of the responsibility of the scheduler to destroy the task when it's no longer needed. So if a thread returns from the function itself and then the scheduler tries to stop it, then we get into problems, at least on FreeRTOS. And then also another thing which we'll get to in a minute is that the task should probably delay itself or have some sort of a condition to block. Otherwise, you can imagine that a task is just always in this running state and it doesn't really ever surrender the CPU to other tasks. And this is a common problem that you'll find on systems or in programs that are poorly written, in that some sort of threads can sort of take control of the CPU and they sort of hog it, and they starve other tasks on the system. But anyway, let's start writing a couple of demo tasks functions now. So we'll create demo task 1, and it will be taking a void pointer, and we'll call this, PV parameters. And then we'll create exactly the same thing again, and we'll just call this one demo task 2. So now we have our two tasks, and what we know from them is that they should have some sort of a loop. So here we have, for instance, some initialization code. In this one, it's just doing some checks, because when the task is actually started, this function gets called. And so as you can imagine, any code that happens before this, for this sort of infinite loop, gets run once. And we can think of this as the task initialization code. So it should do any checks, sort of variable initialization, and in this case, they're doing some sort of a check, right? And so we won't really do any, but we'll just put in a comment init or task init code, just for your reference. And then we'll create an infinite loop. So here they've used an infinite for loop, but we'll just make it even simpler and just do an infinite while loop. And therefore this should never exit or never sort of finish, and so we should never get here, right? Same goes for here in our main loop. We can see that there's this call here, and what this actually does is it starts the sort of loop of the scheduler taking control of our program. So this is the FreeRTOS scheduler, and the name of the function is quite obvious. And so we should never actually get past this function, because on an embedded system, which usually will have one sort of function that should carry out indefinitely, the scheduler should always just keep running and doing its thing. So we should also never get here, right? So let's look at the infinite loops that we have. And we'll create one here as well, the same deal. While 1. And what we can actually do is we can put in maybe like a little print statement. Hello, or let's just say starting task 1. And we'll just take this guy and put him here. There we go. And so those will get run once, and then we'll just put in another print statement here. Hello from task 1. And then we'll take the same thing and put it down here. Now, we're going to run into a problem if we run this. And so let's actually make this, or we have to first create our tasks completely. So what we're going to do is then finish creating our actually we have the functions form now we need to create the tasks. And so we look back at the documentation, the next function it takes is a name, and we look at here, it just says a descriptive name for the task. This is mainly used for debugging. And so it really is. It's not really ever used. It's just really easy for a human readable identifier. So we'll actually put in X, is it called X task create? Yes, here. So we'll take in, firstly takes in the task, the function that it should call. So this is demo task 1, some name. So we'll just call it 1. Next property it takes in is the stack size. And so this is really useful on embedded systems where you sort of are telling it how many words, not bytes, that are being allocated for this function stack. And this works in the same way as when I was talking about stack and heap, in that when it enters a function, some stack is allocated. But the difference is in this case, you can actually give control to how much memory should be allocated. Now on my laptop with gigabytes of RAM, this is not really a problem if we allocate, for instance, here, which I have as a sort of a default, 2,560 words. Now this is, a word is what, like 4 bytes? So this is almost a megabyte, or is a word, no, a word is 2 bytes. So this is about half a megabyte of memory for this task. So this is more, or sort of the amount of RAM that a lot of embedded systems actually come with, and so this task would never work on an actual embedded system, or it'd have to be a very powerful microcontroller for this to work. So now we'll just put in this define, and for those that don't know or haven't really had any exposure to these, we talked about defines in the preprocessor portion of the sort of build process. And what happens is everywhere that this word appears in my code, it's replaced with this. And so I'm just going to put in stack size here, and when this code is compiled, this will essentially be copied and pasted into here, so that xtask create is called with a stack size of 2,560 words. So the next parameter then is PB parameters. And so these are actual parameters that are passed into this function here, but we don't want to pass in anything, and so we'll just put in null. Priority, and so I have the same thing. I have a generic sort of a definition or define here that's just giving me a generic priority, and I'm using a sort of a, this is also a common value or a define from FreeRTOS itself, and this is the lowest priority on the system, which is the idle priority. So we'll just put this in here, main generic priority, and the next thing it needs is a handle. Now the handle here is used for when we want to call control functions for task control, such as the delay functions. Now they take in a handle, as we'll see here, suspend and resume functions, they take in a handle to actually control the state of the task. So we need to be able to reference the task, and what FreeRTOS does is it provides us a handle, which is passed in as a pointer to this create task. But we need to make these variables now. So actual handles that we'll use to reference the task when we want to perform certain control things. So we'll say we need a task handle here, and we'll call this handle 1. We'll set them to null just to be safe that they're not got random stuff from memory in them. Handle 1 and handle 2, and then we'll then pass these ones in to handle 1, and this needs to be a pointer because we'll see in the documentation that there's this little asterisk here. So what we're doing here is we're using the ampersand to actually put in the address of handle 1, thus making a pointer. So quick reformat, and then we'll do the same thing for 2. So we'll put it in task 2, and down here, handle 2. So now we have our 2 tasks created. So we'll go into, where are we? We're in task 1, build, cmake, and then we'll run make. And if we run this, we'll just see that task 2 is getting a bit of control, but there's sort of a bit of spam going on here, that we're not getting this nice 1, 2, 1, 2, 1, 2. And so the problem is that the tasks aren't actually pausing between each execution cycle and sort of saying, okay, I'm blocked, scheduler, maybe you can run something else now. And so what we do really want is to go hello from task 1, hello from task 2. So they sort of, because they've both got the same priority, we want them to sort of share execution. And so this is, as I mentioned in the lecture notes, the problem of our two tasks not having any sort of delay or blocking event in them that actually will then send them from this running state to a block state. So essentially what the scheduler is not really ever taking these running tasks and returning them to ready, like on a periodic basis. And so we need to add in some delays. And so the simple way of doing this is that we just use vtask delay, which just tells the task to sleep for a certain amount of ticks. Now, I think we covered briefly in the lectures what a tick is, but the tick is the basis or the unit of time that the kernel, in this case FreeRTOS and its scheduler, use as its passage of time. So on an embedded system, the tick is generated from hardware, and it's done by using a peripheral called a timer. And so a timer is a piece of the hardware. It's actually on the silicon, and this timer is configured to count to a certain number, and so it takes the CPU clock in and it counts and it counts and it counts, and when it reaches this number, it triggers an interrupt. And so we briefly talked about interrupts, and an interrupt is essentially a hardware signal that is sent to the CPU and interrupts it. It says, hey, I have a signal for you, and it invokes a certain callback function, or what's called an interrupt handler. And the interrupt handler on a board using FreeRTOS is configured then to invoke the scheduler, meaning that this peripheral counts to a certain number, it triggers an interrupt, and this interrupt invokes the scheduler. And so generally, we configure on a lot of embedded systems, like for instance what we use at TUM in the sort of the similar courses, is that the interrupt is configured to interrupt the CPU every millisecond, meaning the scheduler is periodically every millisecond invoked. And this is what we want. And we have a very similar thing here, but we're using software interrupts because we're not actually using like hardware. Like this is not running directly on the hardware. We're emulating this in software. And so the scheduler on this emulator is also invoked every millisecond, but by using a software timer using the Linux kernel APIs. And so what it means here is by ticks to delay. And it's because we have a 1 millisecond tick, we are really having, so every tick that we put in says that I want to delay this task for 1 millisecond. And so we can do this by just saying, we want to, let's say, like have a 1 second delay, so 1,000 milliseconds. So we'll just put vtask delay. So if we have it here, say 1,000. And for instance, what we could do is we could delay demo task 2, vtask delay, to be like 2,000, so every 2 seconds. Now if we run this code, we should have a bit of a different output. So we'll see that we have this sort of double execution of task 1, which makes sense because it's being delayed every second, whereas task 2 executes every 2 seconds here. And so now we have sort of an equal sharing of the CPU in that we have this 1, 2, 1, 2. Right? And so we have our starting task. So these calls are executed once, as we can see from the initialization code. But so this is a little more, like a little fairer now. So what's actually happening is that these tasks are going from running to the blocked state, because if we see here, what this function does is that you want to specify the time that the task remains blocked. And so it will unblock relative to the time specified, right? So we'll say, like, for instance, the task is running, it prints hello from task 1, and then I'm saying, okay, block for 1,000 ticks. And so this task will enter the block state for 1,000 ticks, and then once 1,000 ticks has happened, this event, so this, hey, you've reached 1,000 ticks happens, and it gets put back onto the ready list, and the scheduler can then schedule it and it executes again. So it gets put into running, and it'll execute again. So we can sort of have a look at this because I've written a function to actually print the status of the tasks. And so I think I called it TUM in the futils print task state list, this guy. So we'll just put in a quick print here. And if we just make and run this and just sort of run it really quickly, we'll see here that we have these two tasks being created, and they're both in the ready state. So this means they're here ready to be run. But then if we go and print, for instance, this in the initialization of task 1, we'll see one more thing, and that is this task here, the idle task. And now, the idle task is a task created by FreeRTOS to be run when no other task is ready to be run. Because as you can imagine, the program itself, or on like an embedded system, the CPU has to be doing something all the time. Like you can't just turn the CPU off if there's no tasks to be run, because we still need to, count time, check for these events and whatnot. And so there is this idle task by FreeRTOS that is a default task that does nothing, and it is actually put onto the CPU running when there's nothing else to be done. So essentially, when there's no tasks to be no tasks that are ready, this idle task is always ready and will be put into run, right? And so we can see here we've got this extra task. 2 is in the block state because it's probably already hit hello from task 2. It has already executed this statement and has already hit vtask delay, which blocks it. And so we can actually see here that it's in the block state, right? So if we let this run a little bit further and put this, for instance, inside of task 1 so that it's run periodically, block, but it's a common denominator. We should remove that. So we'll give this a non-common value of let's say 800. If we run this, we should see at some point, I need to make it a little more, no, we still need to change this value. So let's make this really quick and say 300. Okay, actually, scrap this. We'll do it a different way to guarantee that we get it printed. We'll take this and we'll print it out here as well. So now we can see when task 2 executes, for instance here, this little snippet, this shows what is happening in the second of task 1 running. So task 1 is running because it's invoked this call to print out the states, and task 2 is blocked. But then once task 2 actually runs, when we get this code here after task 2, we can see that task 2 is back in the running state. And so all it's showing is that it's going to running, it's blocking, and this event happens to get it back into the ready state, I should say, and then it's run again. So this should hopefully sort of outline how this little loop of states happens, and how we also set up the code for running tasks in a very basic way. Now these tasks can be controlled manually using these control functions, resume and suspend. For instance, if we take vtask suspend and we actually put in a call at the beginning, we can stop the actual calling of task 2 because we can put it directly into the suspend state, which means it's suspended and is not in the ready state to be scheduled, so meaning it will never be run. So if we look at this vtask suspend, we'll just use vtask suspend, perfect, at the top. And now it takes in the handle, not a pointer to the handle, but it's the handle itself. So we want to say, hey, yep, suspend handle task 2. And so we'll actually copy this and paste it here. And then if we make this and run it, we should see that here we have the task created, they're both in the ready state. And then here, this vtask suspend has put the task 2 into the suspend state. So this means that it's never going to get run, because if we run this code, hello task 1 is just printing, and this task 2 stays here in a suspended state. So what we need to do to get it to run is that we need to put it back into, we need to use vtask resume, which it should be documented, and say, resume suspended task, we'll make it available for running again, blah, blah, blah. So here, let's do a quick, we'll initialize an integer here called I. And what we'll do is we'll just put it in a little if statement. If I ++ equals 3, vtask resume to handle 2. And so all this is doing, it's doing a little conditional check. Oh, I've got a single equals, I need double equals. it's doing conditional check, and the plus plus here means that after the check, this value will actually get incremented. So essentially it'll take 3 ticks or 4 ticks for it to get to 3, and then it will resume task 1 again, 2. And so if we run this, hello from task 1, task 1, task 1, and here we go. So now we've gone from it being in the suspended state to actually getting resumed, so that it's running for the first time. We have the initialization code getting run. And then task 2 is running. And as you can see here, task 1 is obviously finished doing its little thing, so it's currently blocked. And then we get down to here, for instance, where all of them are in the ready state, and they'll all be scheduled. And as you can see here, task 1 finishes its execution, and then it enters the block state, task 2 runs and enters the block state here, and task 1 is already ready to be woken up again. So hopefully now we've covered pretty much the entire API for the tasks, and you should have a basic understanding of how we create some tasks here.